Okay, ready? Okay, let's go.
Yeah.
Yo, what up, Vlog Squad? Let's go!
So no one told you life was gonna be this way. Your job's a joke, you broke, your love life's DOA. It's like you're always stuck in second gear, when it hasn't been your day, your week, your month, or even your year. But I'll be there for you. I'll be there for you, 'cause you're there for me too.
Dang, I really don't know what it is. Can you give me a clue?
It has something to do with physics.
I knew it. The jelly donut, isn't it? Jelly donut. Okay, well, can I at least call a friend?
Sure.
Becca! Momentum!
What?
Momentum! Bro, it's momentum.
Momentum is mass in motion, essentially a quantity of motion. We can find this by multiplying the mass times the velocity. The only way that momentum is considered conserved is if the system is isolated, meaning that a group of objects only interact with each other. If the system is not isolated, there is no conservation of momentum. Therefore, there is an impulse. In regards to the types of interactions objects have with one another, there are three types of collisions. The first one is an elastic collision, when the objects separate after the collision. An inelastic collision is where objects do not separate, essentially sticking together. The third is an explosion, where one object breaks into many different pieces after the collision. In regards to how energy and momentum work together, the type of collision needs to be known. In any case, if it is an elastic collision, kinetic energy is conserved, whereas kinetic energy is converted into other forms of energy during an inelastic collision. However, in both cases, if the system does not receive an impulse, momentum is conserved.
Now, we can show this by using an experiment. On this side of the rink, we have Julia! And on the other side, we have Katie! Who will win this battle? In 3, 2, 1! Now that that's over, let's get to the physics side of things. In this situation, the system is the ball and the person. Here we have before the collision. Neither of them are moving, but they're standing at a distance facing each other. There's potential energy, but there is no kinetic energy because they're not in motion. This potential energy will give you the net energy here. In this next part, this is before the collision happens, but they're running at each other. There's still potential energy because the system hasn't reached its maximum velocity, and there's also kinetic energy now because they're in motion. This will give you this net energy, which is the same as this one. We also have momentum in this situation because we use the equation P, which is momentum, equals mass times velocity. You take those values and we'll get the momentum of Katie and the momentum of Julia to get the net momentum. And this is when the collision happens. We have no more potential energy because the system has reached its maximum velocity, but we do have kinetic energy because they're still in motion. This will give you the net energy here, which is the same as here and there. We'll also have momentum. We have the net momentum here, which will be these two, which will be equal to this net momentum. And we get that using the same equation, P equals m over v. Now we're going to discuss what would happen if there's an impulse on an isolated system. Here we have an isolated system.
Hi again! I've been told not to be boring, so I'm going to show you a fun video to demonstrate momentum.
I am an isolated system.
And there you can see we had an impulse.
Now let's discuss what would happen if you take an isolated system and add an impulse. In this situation, Katie is the isolated system and I'll be the impulse. You can see on the graph that Katie has potential energy because she's just taking off when she's running. So she still has potential energy, but she'll also have some kinetic energy because she'll be gaining velocity and she'll be in motion. That'll give you your net energy here. Here you can see the impulse, which occurs right here when I throw the ball at Katie. This will affect the energy at the end. So we have the potential and kinetic energy of Katie, and then we have to add the potential and kinetic energy of me. Taking all these together will add up to this, which will not be the same as this one because of the impulse. We'll also have the momentum just like the other ones. You'll have the momentum of Katie, which will give you the net momentum. You'll have the impulse, and then you'll have the net momentum of Katie and me, which will add up to the net momentum at the end, which will be bigger than the net momentum here, again, because of the impulse.
To recap, momentum is conserved when the system is isolated, and it doesn't matter what type of collision it is. However, the conservation of kinetic energy depends on the type of collision. Thank you so much for watching this video. We hope you enjoyed it. See you next time. Bye!
Bye.
Bye! Change in energy in an object. We can show this by using an equation.
That's boring!
Ow.
Oh my god. Oh my god. Wow, you got him. Wow! I got it.
Your time. Bye. I have to redo it.
That was an inelastic collision.
You look weird. I knew.
Julia just like staring out the window. I'm just like dead staring at them.
I told you it wasn't them. I literally saw them from afar.
That's because they all look the same.
No, they don't. This is. I have to pee again.
I am an isolated system. I am an isolated system. I am an isolated system.
Oh my god. You got that? You're so strong, you broke it in half. This next part of our vlog is called We Complain About John.
PSA.
PSA!
Okay, here's the thing. Here's the thesis. No one bullies John, but John bullies others.
Mind blown. Katie, what do you have? Hey guys! Shy.
I was just like, no. Welcome to Oh, we need food. We just need to.
No, Julia, oh, no, no.